Okay, so we can keep going from Thursday's lecture. Can I? I've been getting a lot of emails from people. Somebody want to sit on this for the lecture? Anyway, is this something I'm doing stupidly, or am I showing that I've never used the whiteboards or the blackboards here? So I've been getting a lot of emails from people saying that they can't find the lecture notes on LMS. They're the PDF lecture notes. Can everybody see those or find them? Yeah. Pardon? Yeah. They're in the resources. And then the lecture slides was my problem. I was having trouble getting LMS to work. But now the PowerPoint lecture slides for these first 3 lectures are up on LMS. And I'll try to be more together next week so that I get them up there in advance so that you can kind of flick through those PowerPoint slides before the lectures. Okay, so this is going to be annoying. Anyway, you can look at the other screen, all right? So where we got to on Thursday's lecture was that we'd kind of pruned, we'd very kind of aggressively pruned down those Navier-Stokes equations. So we had this simpler, we had this simpler set of expressions, okay, which were conservation of mass and conservation of momentum in the x and y directions. So, and as I was trying to explain to you, those conservation momentum equations are just Newton's second law, okay? And please just go through that process or go through that exercise of just quickly deriving that equation for your own sanity, okay? It's just F equals ma. The only tricky term in there is the force term, which is just due to the pressure gradient acting across that kind of control volume of fluid. If you set that problem up correctly, it's very, very simple to nut out that, well, in this case, that x component Euler's equation. You've just got a force due to pressure, and then you've just got mass times acceleration. And we showed that the acceleration in the x direction is just the total derivative of that streamwise velocity component u. And so you can very simply get to those 2 expressions shown at the bottom here. And then at the end of yesterday's lecture, we were dealing with conservation of mass, okay? So du dx plus dv dy equals 0. To me, when I stare at the algebra, I don't get much physical insight by looking at that partial differential equation. But if you go through the derivation, you'll never forget exactly what that expression is showing you, okay? And it's very simple. It's just, that equation is just a complicated way for incompressible steady flow. That equation's just a kind of complicated way of showing that whatever flows into our control volume has to flow out, okay? So as long as we budget the mass flow, that mass flow rate into our control volume, which occurs at this side face and at the bottom face of that control volume, as long as we equate that to the total mass flux out of that control volume, which occurs on that side face and on that upper surface of that cube, you should be able to nut out that expression for conservation of mass, okay? So conservation of mass is kind of an important one for this course, okay? It's always one of the governing equations that whatever fluids course you use, it's always one of your governing equations that you're going to be referring back to. But it's got this very nice kind of intuitive meaning, okay? It just says that if we have some kind of, and I'm supposed not to be using my arms to point for the people who are watching at home in their underpants during SWAT vac, okay? So can you see my little arrow? Probably not in your stress of watching 36 hours of lectures in 1 week, okay? But we've got flow coming in through control surface A on that control volume, okay, and I've got this simple case where there's flow coming out through control surface B, okay, and this is so simple it's insulting to you, but it's nice to remember what conservation of mass is, okay. So now, if I somehow obstruct that flow of fluid coming out through control surface B, say I put my hand there, or my face there, or say it was the nose cone of an aircraft or a rocket, or the front of a building or a wind turbine, if I somehow obstructed that flow that was moving out of control surface B, that equation just tells me that if there's less mass flux coming out through control surface B, and there's the same mass flux going in through control surface A, that flow just has to squirrel out the sides, okay? That makes perfect sense. And that's very intuitive, right? You know that's how fluids behave. If I got a big squishy container, say a gallon milk jug, and filled it with water, and I squeezed it in one direction, it's going to expand in that other direction, okay? Intuitively, you know that that's how fluids behave. They kind of part and move around objects. That's what they want to do. And I guess that's an embodiment of conservation of mass in some sense. So this is the picture for this first half of the course where we're dealing with incompressible flow. For the second part of the course, when we start to deal with compressibility effects, weird things happen, okay? In that case, if we back up and we've got this same scenario, stuff flowing in through A and stuff flowing out through B, when we've got compressibility effects, which remember could occur when we were moving very quickly in air and can't really occur at all in water. So if we're moving quickly in air and I then obstruct that flow coming out through control surface B, we've got this odd situation that can occur. Okay, so again, we restrict the flow at B, say with the nose cone of an aircraft. When you're moving fast enough, you can get this odd counterintuitive scenario that you get a build-up of mass within that control volume, okay? Which means that the volume isn't changing, so the density of that flow is actually changing. So in that case, you can restrict the flow out of B, and rather than that fluid just squirreling out around the sides, okay, you can actually just change the density of the fluid in order to preserve conservation of mass. That probably makes little sense to you at the moment, but that's the premise that we're going to work on for the latter half of this course. Okay, so anyway, we've got that simplified set of equations. We got there from pruning down the Navier-Stokes. We could have just as easily derived them with some simplifying assumptions from that control volume analysis. So at the moment, that set of equations are in Cartesian coordinates. We're also going to require that same set of equations in cylindrical polar coordinates. It's going to, believe it or not, it's going to make life easier for us at certain points through this course. So you've all come across cylindrical polar coordinates in other courses. Yes, one of you has. That's not a bad average, I guess. One out of what's supposed to be 179, but it seems to be a lot less. It seems like the weekend starts early for lots of people. So in Cartesian coordinates, we just define a point in space P in terms of its x and y position from the origin. Okay, so I can define location in terms of that x and y coordinate pair. And then, as we've been discussing so far, there's this associated velocity component with that Cartesian coordinate system. So we have a horizontal component of velocity, lowercase u, which acts in that x direction, and a vertical component of velocity v that acts in that y direction. So that cylindrical polar coordinate system is also very simple. We just define that position P in terms of a radial position, R from the origin, and also, this is definitely going to be one of those days, okay? Also an angular position. I was just thinking how much I like this lecture theatre compared to the others, and then it's kind of It's giving me no love back. Okay, so we define that point P in terms of radial position r and an angle theta. Okay, and we also have to define these two new velocity components, which are the radial component of velocity, which I'm calling u sub r, and the azimuthal component of velocity u theta. Okay, it's making sense. So all I want to do is convert that set of equations from Cartesian to this new set of this new coordinate system. So, and obviously there's a relationship between the two. Okay, you can see that x is just going to be r cos theta, and y is just r sine theta, and then if I put those two velocity systems on top of each other, if you stare at it for long enough, you should be able to see that there's a relationship between u and ur and u theta. Okay, so it's pretty obvious here that the horizontal component of velocity u is just made up of the horizontal component of that radial component of velocity minus that horizontal component of that azimuthal component of velocity. All right, it's just trigonometry. I say it's just trigonometry. It's disgusting, but it is trigonometry, which you've been using for many years now. Okay, so we've got there are three options available for us in terms of converting that set of equations to cylindrical coordinates, and in order of laziness, I'll list them. The first is you can just take my word for it that this is a set of equations: conservation of mass and conservation of momentum in that cylindrical polar coordinate system. Okay, so we're going to use that set of equations, but for now the only thing you really need to know is that we've now got F equals ma applied in that radial and azimuthal direction. So it's conservation of radial and azimuthal momentum. You would never need to learn that set of equations, by the way. They'd be given to you if you ever need them in that full form. The other option is that you can just straight up derive them within that cylindrical coordinate system, which to my mind is also a pretty straightforward approach. Or you can do a coordinate transformation, okay? And you can kind of take your pick with that. I guess many of you might use a Jacobian type transformation, or you can just write this out longhand. Okay, so rederiving them is quite straightforward, and I'll just very quickly show you how that goes for the conservation of mass equation. Okay, so we derived that equation in the Cartesian system using that simple cube-like element of fluid, and we just equated that the mass flux into that control volume had to be balanced by the mass flux out of that control volume. In that cylindrical polar coordinate system, we just do exactly the same thing. We've just got a slightly weirder shaped control volume, okay? But it's really exactly the same process. So we've got this element of fluid. It's located a distance r from the origin. It's a small, a very small element of fluid. So I'm going to call that arc length d theta to show that it's just a very small arc length. And I'm going to call that length of that element dr. Now, the only complication here is that these two sides of the control volume are going to be different under this axis system, okay? So that inner arc length, and you know this from small angle approximation, is just r d theta, okay? And that outer arc length, which is probably where the messiness comes from, is going to be r plus dr d theta, okay? Which just introduces some extra complexity into the algebra. And then we've got a radial component of velocity flowing in through this inner arc surface. We've got that radial component of velocity plus some small change to that velocity flowing out through that outer arc surface. And then through the lower surface, we've got that azimuthal component of velocity flowing in, and out of the upper surface, that azimuthal component plus some small change. Does that make sense? Everyone could set that up, right? I mean, everything else I do is really, really straightforward. I think the important thing is that you could draw that sketch and you could kind of write out these terms. Once you get there, everything else is plain sailing, okay? So then it's just mass flow, the mass flux, which is a rate of mass flow. So the mass flux into the element must equal the mass flux out, okay? So mass flux in is quite simple. Remember, the mass flux is the volume flux multiplied by the density, all right? And I'm going to keep saying that until one of you gets angry with me, because it's absolutely critical for every topic in this course. All we do throughout this course is apply conservation of mass, conservation of momentum, and for the latter part of this course, we also use conservation of energy. Everything we're doing is based on these conservation equations, all right? So mass flux in is just going to be velocity times area of that control surface multiplied by density, okay? So we've got rho UR r d theta flowing in through this inner surface. We've also got mass flux in at the bottom, which is going to be U theta, rho U theta dr. And then we've got mass flux out through that outer surface, which is just the velocity times the area times the density at that outer surface, which is a little bit more complicated algebraically. And we've got mass flux out through that upper surface, which again looks nasty, but is just density times velocity times area, okay? So what happens here is that some of those terms drop out immediately. And when we multiply out those brackets, we're left with this behemoth at the bottom here, okay? So there's... I was supposed to quiz you on that, and then I leant on my keyboard, and that red square appeared. So one of those terms is smaller than all the others, okay? And you know about that. You know that products of small changes are going to be orders of magnitude smaller than that small change itself, okay? So this particular term is dr squared d theta. All of those other terms are just dr d theta. So that one that I'm highlighting is going to be orders of magnitude smaller than all of the others. You're familiar with doing this from other courses, right? These equations, especially in the latter part of the course, are going to get really nasty. But by recognizing which terms are insignificant, we can keep everything manageable. So when we get rid of that term, we see that everything else has this rho dr d theta in it, which we can just get rid of. And very simply, this version of conservation of mass in that cylindrical polar coordinate system drops out. So does that make sense? It's a little bit more tricky if you try to do conservation of momentum, but at least you can see where these equations are coming from. The other option, and I guess we're going to use this later on in today's lecture, is that you can just transform them. And I'll show you how to do this longhand. It's very straightforward. It's just not a particularly good spectator sport and not much fun, okay? So using the chain rule, I can write that du dx is just equal to du dr dx plus du d theta dx. And likewise, I can write that dv dy is just equal to dv dr dy plus dv d theta dy. It sounds like the most boring song you've ever heard, okay? And then you can poke those back into that equation at the top, and you end up with this, not very fun-looking expression at the bottom there, okay? But that's made up of the products of 8 partial differential terms, which, if we remember our relationships between cylindrical and Cartesian coordinate systems, we can easily write out expressions for each of those terms, okay? So, for example, if we take this du dr term, we know this relationship between u and the radial and the azimuthal component of velocities and that angle theta, okay? So I can easily write out an equation for du dr, okay? Again, it's not a lot of fun. I have to expand it using the product rule, but you've got to be clever again, okay? These terms, these partial differential of those cosine terms with respect to r are just 0, okay? You know, the angle doesn't vary with radial position, so those partial differential terms just disappear. And you can do this for every one of those terms, right? You can write out an expression for du d theta, dv dr, and dv d theta. Is it looking like it's going to be fun yet? So that's 4 of those terms taken care of, and then we can also write out expressions for those other partial differentials, okay? So these are a little bit more simple. So you've got you've got relationships for r and theta here, so you can write out an equation for dr dx. Is everyone following what I'm doing, roughly? I'm just differentiating that equation for r with respect to x. And you can see that that just becomes x on r. What do we know that x on r is in terms of theta? It's something, right, in terms of theta. All right, okay, it's cos theta. But my point is that if you weren't kind of all semi-comatose and were actually paying attention, that you can, if you take those terms one at a time, you can write out expressions for them, okay? And I'm certainly not suggesting that that's fun, okay? So all of those terms, dr dx, dr dy, d theta dx, and d theta dy have simple expressions. And when we plumb all of this back into that equation at the top, you end up with this beauty, okay, here. And then if you don't, you know, if you were feeling positive that day and you didn't just kind of off yourself or decide that you weren't going to do this problem anymore, you could see that some of those terms just cancel out, okay? And then you've got this beautiful result here. And what do you know about cos squared theta plus sine squared theta? It's amazing what you store in your brains, huh? So, and then you very rapidly get to that version of conservation of mass in that cylindrical polar coordinate system, all right? So it's not fun, but it's possible. And I know that those of you who are more into mathematics, there's more elegant ways of affecting that transformation, but you've got to know what you're doing, okay? All right, so we've got a set of equations. We can deal with Cartesian and cylindrical polar coordinates. The only other thing I think that I need to reintroduce before we keep going is this concept of streamlines, okay? So a flow field is usually defined in terms of the velocity, okay? And that velocity has a magnitude and a direction, okay? So I could represent the flow around this aerofoil in terms of a vector field, okay? So I've got all these little vectors which show me the flow around that aerofoil. So you've learned about streamlines in your introductory fluids course, but again, I'm just going to assume that you've forgotten that. A streamline is just a line that's parallel or tangent to the local direction of those velocity vectors. Does that make sense? You have come across streamlines, right? You've used them. This is very disturbing because I know you've all used Bernoulli's equation. That's only applicable along a streamline, okay? Which makes me think most of you don't. Most of you are just applying Bernoulli's equation in iffy situations, okay? So I could replace that vector field with a bunch of lines, which are defined as streamlines, okay? And streamlines are useful for us as engineers. I mean, if I'm working on a problem, you know, if I'm working on this MUR motorsports problem, and I want to know what the flow around that car is doing, if I knew the streamline pattern, I'd have a good sense for what that flow was doing around the car, okay? So engineers often try to visualize streamlines. We stick on tufts of yarn or tufts of wool onto the body that we're interested in, and they're going to align themselves with the flow direction, okay? And it gives us a kind of a way of visualizing would otherwise be an invisible flow, okay? And do any of you sail? No. Any of you? No. Okay. There was a time, I imagine, when I could have asked that to a class of mechanical engineers and I'd have got a pretty decent show of hands. But anyway, so in sailing community, they're called telltales, and they're often stuck onto the sail so that the sailor knows how their sail's performing, okay? So this is quite a nice example of that. They've tufted this, NASA have tufted this aircraft to try and then they've obviously followed it in a chase plane and filmed it, and they're trying to see or instantaneously visualize what the flow around that aircraft is doing. And actually what you can see is that the aircraft or the aerofoil is stalled. Those tufts of wool are no longer following that expected flow direction over the wing. You've got this, I've lost my cursor, you've got this large-scale circulation over that wing if you look on the pattern. So that aircraft's kind of operating in this very dodgy high stall condition, but evidently doing quite well. So streamlines are useful for us as engineers, okay, and they're parallel to that local velocity vector. So I guess that kind of wall tufting would be, those of you who are involved in that motorsports capstone project, wall tufting is a pretty useful way to go rather than going straight for the CFD or straight for the wind tunnel experiment. If you want to know what the flow's doing into your cooling boxes where the radiator is or over your front and back wing, that's a pretty kind of, that's a kind of $2 attempt at having a first look at that flow. Very cheap and easy. So on page 9 of your lecture notes, you were asked to prove these equations for a streamline, okay? I'm actually just going to show you. There are a lot of these exercises in the lecture notes, and I'm not going to do very many of them, but this one's of particular importance, so I'll just show where that comes from quickly, okay? So I would use those exercises in the PDF notes to supplement the tutorial problems that you have, okay? You should also be able to do most of those exercises in the notes pretty easily by the end of this course. So anyway, we'll give you one for free. So there's this streamline, and we want to derive an equation for that streamline in terms of the velocity components. And it's very simple. I can take some element on that streamline ds, okay, and we know from our definition of a streamline that that element ds must be tangential to the local velocity vector, which I'm going to call v, okay, and I'm writing this out in vector notation, okay, so ds is just equal to dxi plus dyj plus dzk in three-dimensional space, and that capital V tilde vector is just ui plus vj plus wk in 3 dimensions, okay? So I know that ds and dv are parallel to each other or tangent to each other, so what vector operator should I use to prove this equation? Cross product, this. So if I take the cross product of these two vectors and they're truly parallel to each other, that cross product should be 0. Okay. So ds cross v is equal to 0. I know that they're tangent to each other, and that's very, very simple. Okay. You can see that that ith component here is just going to be w dy minus v dz. And you can see that that kth component is just going to be v dx minus u dy, and likewise for that jth component, okay? And all of those have to be 0, or all of those, in all of those 3 vector dimensions, those products have to be 0 if these two, if ds and that vector v are genuinely tangent to each other. Okay, so you just end up with 3 equalities for 3-dimensional flow. And we've already said for this course that we're only dealing with 2-dimensional flow. So these top 2 expressions that involve w and dz, just disappear. And we've got this one expression that we're really interested in for this course, which is the equation for a streamline in 2 dimensions, which is just that v dx minus u dy is equal to 0. Okay? Have any of you come across that expression for a streamline before? Okay. Yep. Don't just say yes to make me feel better. All right. So I think I've kind of introduced most of the basic building blocks that we need so that we can push on with this course. And I've told you I'm going to be jumping around for the first couple of lectures. And the reason is that I'm going to use this test case or this test problem as a kind of vehicle to introduce the concepts of potential flow. I've taught this course quite a few times, and I think it works better that way. Okay? So I'll try and remind you where we are in the notes. So the problem's very simple. It's this smoker's problem. Okay? We've got these 2 people who are having a cigarette. Okay? So they're creating a contamination. And the question is very simple. I'm going to add... it's very simple, and it's a problem, I guess, that many airports deal with. I'm going to add an extraction fan. Okay, so I'm going to remove mass flow from some point in space, and I want to work out where's the safe limit for somebody else to stand and not be contaminated by that cigarette smoke. Okay, so the question is, how far does the non-smoker need to stand from the smokers to avoid the secondhand smoke? Okay, so that language, I think, is very much of the kind of anti-smoking community. Okay, so not to be discriminatory, because I know that probably some of you smoke, we can pose it another way. How far would the smokers need to stand from the non-smoker to avoid giving them free smoke? Okay, it's exactly the same problem. It's a serious problem, actually. It's one where you've got a release of a contaminant. We're releasing a contaminant, and it could be something that's much nastier than cigarette smoke. I know that anti-smoking lobby would have you believe that cigarette smoke is the most nasty contaminant, but there are worse things. Okay, we've got a release of a contaminant, and we've got some attempt to contain that release contaminant, okay? And then we're going to set up some kind of safety zone or exclusion zone. So it is a serious problem. So we could obviously solve the full 3D Navier-Stokes equations with appropriate boundary conditions, but what I'm telling you is that that's going to be expensive, and I also think in this instance it's overkill because we can get almost the same result with a very, very simple pen and paper calculation, which is what we're going to be heading towards. Okay, so we want to make use of that simplified set of 2D incompressible equations that we've come up with. Okay, so we're going to gradually build to this view, okay, but in actual fact we're not even going to use this simplified set of equations. We're going to attempt to be even lazier and make everything even more tractable for ourselves. And the first thing that we can do is really a trick. We can introduce an intermediate variable that straight off the bat is going to satisfy conservation of mass. Okay, and this is this property that's known as the stream function. Okay, so for now it's just an algebraic construct, but I'll show you what the meaning of it is. Okay, so we introduce this function psi, which is called the stream function, and we define it such that the horizontal component of velocity is equal to d psi dy, and the vertical component of velocity is equal to minus d psi dx. Okay, so it seems pointless at the moment. We're all comfortable with u and v. We know physically what it means, and then we've introduced this kind of intermediate variable which runs the risk of us getting lost. But you can see that it does have some real benefit. Okay, That minus sign's really important, okay? This equation isn't going to be given for you on an exam or ever as engineers, all right? You're expected to know this, and equally, you're expected to know that that minus sign is there. If you don't get that minus sign there, the non-smoker's going to get contaminated, okay? So it's an important one. So we substitute those equations for the stream function. If we substitute them into our continuity equation or conservation of mass, you get this nice result, okay? So u is equal to d psi dy, so that first term is just d dx d psi dy, and v is equal to minus d psi dx, so that second term is just d dy d psi dx, and you know that the order that we do those differentiation operations or partial differentiation operations, it doesn't matter, okay? It's commutable. So what we end up with is this automatic satisfying of the continuity equation. Does that make sense? So psi is an intermediate variable that automatically satisfies continuity, and there's nothing mysterious about it. It's just saying that I can't make up any flow field and have it satisfy continuity, okay? There's a unique relationship between u and v, or more appropriately, how u and v change spatially, that's required to satisfy continuity. And by defining flow fields in terms of that stream function, I'm kind of guaranteed that I automatically satisfy continuity. Okay? Does that kind of make sense? I only ask because I learnt about potential flow for years during an aerospace engineering course, and I never really understood why people were making things more difficult for me. But actually, they're making things more easy for you, because once you've jumped through certain hoops, you actually never have to go back to those governing set of equations. You just have a flow field that you automatically know straight off the bat is satisfying at least one of your equations of motion, okay? But what does it mean, okay? What's the meaning of that stream function psi? It has a very nice meaning, actually. The first question we can ask is, what's a line of a constant psi equal to, or what's the meaning of a line of constant psi? So it's very easy to write out an equation for some small change in that property psi, okay? D psi is just equal to d psi dx dx plus d psi dy dy. So all I'm doing there is assuming that psi is only a function of x and y, and I'm writing out effectively the total derivative or the total change in psi as a function of those x and y directions, okay? So into this equation, I can substitute my expressions for u and v, okay? So u is equal to d psi dy, v is equal to minus d psi dx, and I end up with this equation here, okay? So d psi is equal to minus v dx u dy. So a line of constant stream function is going to be a line where d psi is equal to 0, okay? So for a line of constant stream function, we get that 0 is equal to v dx minus u dy. And what's that the equation for? Come on, go into the goldfish-like depths of your memory and think back to 5 minutes ago. It's so obvious you're not saying, or you're already halfway to the pub or lawn or wherever you're going for the weekend. It's the equation for a streamline, okay? Did none of you remember that? So it's just I just stand here with words coming out my mouth, and you're... okay, well, I remembered anyway. That's the equation for a streamline, okay? So a line of constant stream function is a streamline. So that means that psi has a constant value along all of those lines that I sketched around that aerofoil earlier, which you also won't remember, I guess. But I did do that, okay? So, and then the other question we might ask is, does the value of psi have any meaning. And it does, okay? And this, again, was something that certainly bypassed me when I first learnt about potential flow. So just consider two streamlines, okay? And we now know that those two streamlines are going to have constant values of that stream function psi all the way along them, okay? And we'll say that one has a value psi1 and one has a value psi2, okay? So to nut out numerically what the value of stream function actually means, we can just consider a line connecting those two streamlines, and we can calculate the volume flux or the mass flux across that line connecting those two streamlines. So what I'm going to do actually is consider some small element, which I'm highlighting in that magenta color, which you probably can't see, and I'm just going to consider the mass flux or the volume flux across that small element, which I'm zooming in on now in this slide. So I'm going to say that that element, that small element, has length ds, and I'm just going to consider the volume flux through this small triangular element that I'm sketching, okay? So the volume flux through that element ds is just the area, which in this 2D approximation is just ds multiplied by 1, multiplied by the velocity perpendicular to that face, which I'm calling here capital V. So conservation of mass, again, tells me that the mass flux into my element must equal the mass flux out of my element. So I've got VDS flowing in, and I've also got VDX flowing in to that element, and I've got UDY flowing out. Okay, does that make sense? So what I can do in that expression is substitute in my expressions for the stream function. Okay, I know that U is equal to d psi dy, and I know that V is equal to minus d psi dx. Okay, and you've got to, as I say, you've got to learn those definitions. So what we end up with is that VDS is equal to these kind of partial differential terms on the right-hand side of that expression. I feel stupid asking now that I know how long your memory is, but what's the right-hand side of that equation equal to? It's 0 if we were moving along a streamline, right? But it's equal to, you're saying it's 0 because it's equal to d psi. I know that you wanted to give me the correct answer. It would be, it's the change in the stream function d psi, and it would be 0 along a streamline, okay? Because the value of stream function doesn't change along a streamline. Right? But in this case, we're moving between two streamlines, so we have VDS is equal to d psi over that small element. And if I just integrate between streamline 1 and 2, which is integrating along that entire blue line sketched in that diagram above, I just get that the integral of VDS between position 1 and 2 is equal to the integral of d psi between positions 1 and 2, which is just psi2 minus psi1. Okay? So what that expression tells us is that if we have streamlines in a flow, all of which have a different value of stream function associated with them, the difference between those two, if I take 2 points in the flow, the difference between the stream function values of those 2 points in the flow is going to be equal to the mass flux, or the volume, sorry, there's no density in this equation, the volume flux between those two streamlines. Does that make sense? I mean, I guess it doesn't make sense why that would be useful, but numerically, the stream function has a meaning, okay? Or to be precise, the way that the stream function value changes in a flow field has a meaning, and it gives us a measure of the local volume flux at different positions within the field, okay? So it's really just an abstraction. It's just an intermediate variable from U and V, okay? All right, so what we need to be able to do is to define the stream function for some simple flows. And actually, these simple flows are going to become our building block flows when we move on through this course, okay? And they're going to get more complicated, but I'm going to start with the most basic flow that I can think of, all right? Which is just uniform flow from left to right on the screen. And I'm going to define that uniform flow has a velocity magnitude U infinity, okay? So in my Cartesian velocity component system, I can easily write that lowercase u equals U infinity and lowercase v equals 0, okay? But what I want to do is get away from that description, get away from that habit of describing this flow in terms of those Cartesian velocity components, and I want to describe it in terms of the stream function, okay? Because if I can do so, I know that I'm automatically satisfying one of my equations of motion, which is conservation of mass. So we know that u is equal to dψ dy. We've defined that. And v is equal to minus dψ dx. By the way, this is on page 31 of your lecture notes. So I can make that substitution, and then I have dψ dy equals U infinity, dψ dx is equal to 0. So what do I do to get an expression for the stream function? Come on, just show me that one of you is not at the pub already. What do I do to get an expression for the stream function now? I've got two partial differential equations for the... Okay, well, what I'm going to do is integrate those two equations, okay? So if I integrate this first equation, I've got dψ dy is equal to U infinity, so psi is equal to U infinity y plus some possible function of x, all right, which I don't know at the moment, all right? And then when I integrate that other equation, I get that psi is equal to, 0 integrated with respect to x is still 0. So I just get that psi is equal to some possible function of y, okay? And by comparing those two equations, you can see that they're only compatible if f2, which is that function of y, is equal to U infinity y, and f1 is just a constant of integration, okay? And by definition, for most flow fields, we say that the stream function psi is equal to 0 when x and y are equals to 0. So you can see in this case that constant of integration is just 0, all right? Does that make sense? You're going to have to be able to do this, so I hope it makes sense. So what we end up with is that the stream function for this very simple flow field is just U infinity y, okay? And because we've been able to express that in terms of the stream function, we know that it satisfies conservation of mass. I mean, it's a stupid flow field, right? A kid could have told me that that satisfies conservation of mass, but we've kind of formally proven it by going through this process, okay? And likewise, we could take a slightly more complicated flow, which would be a uniform flow at some angle of attack alpha, and we could go through the same process, okay? So in this case, the horizontal component of velocity is U infinity cos alpha. The vertical component of velocity would be U infinity sine alpha. And again, we can make that substitution for the stream function, okay? So we get, once we substitute, we get that dψ dy equals U infinity cos alpha, and minus dψ dx is equal to U infinity sine alpha. And we go through the same process of integration, okay? I integrate U infinity cos alpha to get an expression for psi, and I also integrate minus u infinity sine alpha to get an expression for psi. And in this case, you can see, in this case, you should be able to see that the only way that those two equations are compatible is if that function of x, f1, is equal to minus u infinity x sine alpha, and if that function f2 is equal to u infinity y cos alpha. So we've got these two simultaneous equations that we're trying to make compatible, okay, through those unknown constants of integration. So we end up with a simple expression for the stream function for this flow that's at an angle of attack, all right? So I'm out of time now, but on page 34 of your lecture notes, you're kind of asked, as an example, just to nut out the stream function for some very, very simple building block flows. And if you've got a couple of minutes over the weekend, which I can imagine you won't bother doing, you could try to nut out those equations and look a little bit more lively on Tuesday. All right? Okay. To the pub, to the weekend, wherever you're going.
But I would like to understand what's the pi thing,
Yeah. Okay. It was, what do I have to wrong? Let me just turn this off. Yeah, so really it's just the first equation of motion tells us that the first equation of motion tells us that du dx plus dv dy must equal to 0. Okay. So, I'm sure. So, really, all that's telling us is that I can't just define any random flow field and have it satisfy conservation of mass. Okay. So that psi really is just an intermediate variable, which is a relationship between u and v. It's a notation, really, which is a relationship between u and v, which is automatically going to satisfy conservation of mass.
Yeah, so it's like the result component of velocities, for example, in the x direction and the y direction.
Yes.
Oh yeah, that's it.
Yeah. So it's actually just
it's a
notation. It's like an intermediate step.
Yeah.
I mean, but later on it becomes convenient for us, because when we substitute it into the other equations of motion, like this very nice simple result drops out. But for now, I mean, in the next lecture we'll show that we can, with an extra caveat, we can also satisfy conservation of momentum with that psi definition. But for now, it just satisfies conservation of mass. Okay, so. I mean, I think that's the only way to look at it. It's an intermediate variable. So really, it's like we're now, rather than talking about vectors in u and v, we're now talking about the flows in terms of streamlines. Actually, that's kind of, I think that's all it is.
Yeah, and I would like to ask about, because I was checking the first lecture.
Yeah.
There's an assignment which is due week 3.
I think I'll put it out on week 3.
So it will be out on week 3.
Or actually, if I get time, I'll put it out. I'll probably put the first part out next week, because the first part is more.